We've looked at various aspects of quadratics, but one thing we haven't yet looked at is what do the graphs of quadratics look like. So let's investigate the graph of y equals x squared, and we won't assume any previous knowledge. I'll assume that you have never seen this curve before. Well, if we have any equation that we've never seen the graph of before and we want to investigate it, the only thing we could do to begin with is to plot some points and see if we can spot a pattern. So if we have an x value of 0, the value of y being 0 squared will also be 0, so this curve passes through the point 0, 0. If we have an x value of 1, then when we square that we get 1, so the curve will also pass through 1, 1. For an x value of 2, we'll square that to get a y value of 4, so the curve passes through 2, 4. And so on. Let's look similarly at positive integer values of x. We see that it doesn't take long before the values of y go up quite quickly as x increases. Of course, the curve we're looking for is not defined only for integer values, but these are the ones that it's easy to start seeing what the curve is going to look like. Similarly, we can investigate what is going to happen for some negative values of x. If we have an x of negative 1, then negative 1 squared is 1, so the curve will pass through negative 1, 1. Negative 2 squared is 4, so the curve will pass through negative 2, 4. And we can see that for other negative values of x, the y values will be the same as the corresponding positive values of x. Now that we have some points, perhaps we can start to see what the curve that passes through them would look like. Joining them with a nice smooth curve, we have this shape. Let's remove the points themselves so that we can just concentrate on the curve. Here then is a sketch of y equals x squared. You can see that the scale on the y-axis has had to be quite different from the scale on the x-axis so that we could see all of those plotted points. Let's try and restore it to a similar scale to the x-axis. And so we still have the same shape of curve that we had before, just slightly stretched as I've stretched that axis upwards. Here then is a graph of y equals x squared. Let's just emphasize a couple of key points about this curve. Firstly, because of plotting the same y values above the positive and negative x values, for example, above 2 and negative 2, we both plot a 4, there is going to be symmetry for this curve. It will always have a vertical line of symmetry. In this case, of course, that vertical line of symmetry is the y-axis. Another important thing to note is that although the curve heads upwards at an ever-increasing gradient as we move away from the y-axis, it's never going to point directly up. It will always keep curving. So this is a sketch of the equation y equals x squared, but this curve itself has a particular name. We call this curve a parabola. Now that we know what a sketch of y equals x squared looks like, how could we sketch some other quadratics? For example, suppose we wanted to sketch the equation y is x squared, subtract 2x, subtract 3. Well, one thing we know how to do with quadratics is to complete the square. So let's do that to begin with. Instead of x squared subtract 2x, we could write x minus 1 squared, subtract minus 1 squared, and there's still this subtract 3 on the end. So we have that y is x minus 1 squared, subtract 1, subtract 3. In other words, y is x subtract 1 squared, subtract 4. And I'm going to write that as y plus 4 is x minus 1 squared, or y subtract negative 4 is x minus 1 squared. Why write that last part in that particular way? Well, this may remind you of something we did with transformations. If we started off with the equation y is x squared, and we finished off with the equation y subtract negative 4 is x subtract 1 squared, then we have replaced an x by x minus 1. We have also replaced y by y minus negative 4. So what we have done in the first instance is to have a translation of 1, 0. And what we have done in the second instance is to have a translation of 0, negative 4. Now those two translations are independent of each other, so you could really say that what we have done is just a single translation of 1, negative 4. We are using here information from our transformations. The top two lines are the important ones here. If we replace the x with x minus c, we've done a translation of c0. If we replace y with y minus c, we do a translation of 0c. In this case, to get from a y equals x squared curve to the curve that we are interested in, we have to do a translation of 1, negative 4. Let's illustrate that. If we start off with our graph of y equals x squared, but then we do a translation horizontally of 1 unit and a translation vertically of 4 units down, then this new green curve is the graph of y equals x squared subtract 2x subtract 3. The important thing to realize is that this new curve, because it is obtained from the original one just by translations, has all the same properties in terms of symmetry. It still has a vertical line of symmetry, but that line is now in the position x equals 1 because we have done a translation 1 unit to the right. What would a graph of y is negative x squared looks like? Well, if we write that as negative y is x squared, then now it is easy to see how we get from a graph of y equals x squared to a graph of negative y is x squared. What we have done is replaced our y by a negative y. And one of our other transformation rules says that if you replace y with negative y, you have a reflection in the x-axis. So starting with a graph of y is x squared, a graph of y equals negative x squared will look exactly the same, but reflected in the x-axis, so going down rather than up. In fact, all quadratics will have one of these two shapes. It will either be curved going ever upwards, like our original y equals x squared, or curved going ever downwards, like our y equals negative x squared curve. And the thing which will tell those two apart for us is the coefficient of x squared. If we have a positive amount of x squareds, the curve will go up. If it is a negative amount, it will go down. Quadratics are sometimes informally described as always being smiley or frowny. That's all to do with whether you have a positive or negative coefficient of x squared. How would we draw a quadratic graph with a coefficient of x squared other than 1 or negative 1? For example, y is 2x squared. One thing we could do is to rewrite that as y divided by 2 is x squared, and now again we can use our transformation rules. Because to go from a graph of y equals x squared to a graph of y over 2 is x squared, we have to replace y by y divided by 2, and so our transformation rules tell us that we have a stretch. That stretch will be parallel to the y-axis and of a scale factor of 2. We are using one of our stretch transformation rules. Replace y with y over k, and we have a stretch parallel to the y-axis of scale factor k. So if here is our sketch of y equals x squared, our sketch of y equals 2x squared will look like this. For example, where originally we had the point 1, 1, that has been stretched upwards by a scale factor 2 parallel to the y-axis to now be the point 1, 2. Again, note that our new curve has effectively the same shape as our original one. All we have done is stretch it, so we will have maintained the symmetry. It will still have a vertical line of symmetry. The natural question to ask now is, can we draw the graph of any quadratic curve? If I've just got ax squareds plus bx's plus c, could I draw the graph of y equals ax squared plus bx plus c, where a, b and c are any numbers at all? Well, the answer is yes, and the good news is they all look exactly like the curves we have seen so far. If we have a positive value of a, then the curve will look like a smiley quadratic. If we have a value of a which is less than 0, we'll have a frowny quadratic. Now, you do not need to be able to understand or reproduce a formal proof of why this is the case. What you will need to do is know exactly how to sketch these curves and show some key points such as intersections with the axes. That's going to be the content of our next video. So you are quite welcome, if you like, to bail out at this point and go and see what you have to do in practice. But for those of you who are interested, I'm going to go through a proof of why every quadratic curve looks like the ones that we've been considering so far. Let's go back to the beginning then. We are considering a curve y is ax squared plus bx plus c, where a, b and c can be any numbers. And the first thing I am going to do is rewrite this using completing the square. So first, let's factorize out the a from the first two terms, giving me a into x squared plus b over a x's, and we'll still have that plus c term on the end. Now, if we complete the square inside the big bracket, we will have x plus b over 2a squared, subtract b over 2a squared, and then there's still a plus c outside the bracket. Let's now expand that big bracket. Y is a into x plus b over 2a squared, subtract a times b over 2a squared plus c. Just going to do a tiny little bit of rewriting of that final term. Quite happy with the way the first part of this is looking. But that last bit, let's just write that as plus, and in a big bracket, c subtract a into b over 2a squared. The reason I'm doing that is because I'm now going to introduce some new constants. I'll have a constant called p, which is just the same as a. I'll have a constant called q, which is b over 2a, and I'll have a constant called r, which is c subtract a into b over 2a squared. The reason I've done this is because using those three new constants, I can go from my original form. If we started off with the curve being y is ax squared plus bx plus c, then I can instead treat this as y is p into x plus q squared plus c. Why have I done all this? Well, the original form might be an attractive way to look at a quadratic, but it's very difficult to interpret what it looks like. This new version, I claim, is going to be much easier to interpret. And how can we do that? Well, we can do it by starting off with our curve y equals x squared, a curve which we understand well what it looks like, and slowly transform it into this destination. Let's do it piece by piece. We'll start off by saying, if I know what y equals x squared looks like, can I tell what y equals x plus q squared looks like? This curve on the right hand side could be rewritten as y is x subtract negative q squared. So how have we gone from this curve to this curve? We have replaced x by x subtract negative q. Now our transformation rules tell us that what we have done is a translation of negative q, 0. Okay, well, we haven't got to our final destination curve yet. We've only got as far as x plus q all squared. Next, we'll transform that into y is p times x plus q squared. Now we can rewrite this new curve as y divided by p is x plus q squared. So you can see that the algebraic change we have done is to replace y by y over p, and so our transformation rules tell us that what we have done is a stretch parallel to the y-axis of scale factor p. We're still not quite at the final destination that we wanted. We have got as far as y is p lots of x plus q squared. How can we turn that into y is p lots of x plus q squared plus r? Well, if we rewrite that as y subtract r is p lots of x plus q squared, you can see that the algebraic change we've made is that y has been replaced by y minus r, so we have a translation of 0r. The important thing is that we have got from the y equals x squared curve to the y equals ax squared plus bx plus c curve simply by doing a sequence of translations and stretches, and neither of those things, a translation or a stretch, will change the symmetry of the curve. It will look the same as a y equals x squared curve, just in a different position because of the translation, and maybe stretched up a little bit. And more than that, we used the fact that this constant p we introduced was really just the same as the constant a, and the only place in this argument where p has changed the shape of the curve is when we did this stretch parallel to the y-axis of scale factor p. If p was positive, that will mean that the curve maintains its original shape. So if p, therefore a, was greater than 0, then we'll go from a y equals x squared curve to another curve of a similar kind of shape. However, if a was less than 0, then our original curve will not only be stretched by a scale factor, but it will also be flipped over. So it is the sign of a which indicates whether we have a smiley or a frowny quadratic.